To form a useful image, we need to have parts of our object field interacting with light waves differently to other parts. So our image then becomes a representation of those different interactions. The first part of this lecture is talking about some of those most common interactions of matter with light. It'll be a revision because you would have learned most of these in different subjects. However, it'll be good to see them all together in the context of optics. We'll finish this lecture with the topic of how, even with amazing object contrast, we can't always resolve it in our images. When a photon's energy matches that of an excited state of an atom, then the atom absorbs that photon. And if that energy is transferred to other atoms and eventually to heat more quickly than it can be re-emitted as another photon, we say that the absorption process has taken place. This is a dissipative process. If we follow the intensity of light, or the irradiance of a light beam, as it travels through an absorbing medium, we'll see that that intensity drops away. It will eventually reach zero, and that's occurring because energy, light, is being removed from the beam by the absorption process. If we consider the irradiance of a beam of light as it travels through an absorbing medium at two positions, then we can consider how this intensity changes as a function of change in position. By making these changes infinitesimally small, we end up with a differential equation to solve. And unsurprisingly, that shows us that the intensity that travels through our absorbing system is going to decrease exponentially as a function of distance. This coefficient here is the absorption coefficient, and it's characteristic of that material. It also depends on the wavelength of light. In this problem, I'm giving you a neutral density filter which has a certain thickness that the light has to travel through, and only 43% of the incident light is transmitted. Now, the filter is made to be thicker, 3.5 millimeters, and the question is, how much light is transmitted now? We might image an object that has different concentrations of absorber in different locations. In that case, the absorption coefficient is then going to be proportional to that concentration. In the example here, I consider a dye that has been diluted by a factor of 85. What that means is our absorption coefficient is divided by 85, and we can use that to calculate the new transmission. In contrast to the excitation process of absorption, we have another important set of light-matter interactions called scattering, or non-resonant scattering in particular. They occur when the photon energy is not enough to drive the atom to its higher excited state. Nevertheless, we still have an incoming electromagnetic wave, and our atom still consists of a negative electron cloud surrounding a positive core. These feel forces, of course, because of the electric field, and so the electric field is going to immediately cause the electron cloud to oscillate. So what we have is an oscillating dipole, and an oscillating dipole radiates electromagnetic waves. They have the same frequency. So in this non-resonant process, you can see one important thing is that the incoming photon has the same energy as the outgoing photon. No energy is lost. It's an elastic process. Secondly, the photon will not necessarily travel in the same direction. It may travel in a different direction, and that's why we have this overarching term called scattering, which indicates that the light has changed direction. Reflection is actually a form of scattering, and it's one of the most common matter radiation interactions that we use in imaging. And if we want to characterize reflection from material, then we need to understand its efficiency, what percent is reflected, the directionality, does it all come out at one angle or does it come out at a number of angles, and the wavelength dependence. The reflectivity of an object measures the efficiency of the reflection process. It's the ratio of the irradiance of the reflected light to the irradiance of the incident light. I have 3 objects shown at the bottom, 2 of them with high reflectivity and 1, black velvet, with obviously low reflectivity. It's interesting though that both the mirror and white paper, when we observe reflected light on them, look distinctly different. So clearly there's more to reflection than simply the reflectivity. The difference between the mirror and white paper is seen in the direction that the light is reflected. In the case of a mirror, light incident at an angle theta I is all reflected at an angle which is equal to theta I. However, for diffuse reflection, we have light emitted in a large range of angles. If we have a situation where the reflectivity is a constant value at all angles, we have a surface that's known as a Lambertian surface. Because of the complicated atomic and electronic structure of different materials, the reflectivity varies with the photon energy, or as we often measure in the lab, wavelength. In this example here, I've shown a plot of the reflectance or the reflectivity of light over an extended wavelength range. If I highlight the visible range here, 400 to 700 nanometers, you can see why it is that the metals have the colors that we see them to have. Gold, for example, only reflects light in this long wavelength region, the wavelength region containing yellow, orange, and red, and that's why it has that golden color. On the other hand, aluminium and silver both reflect fairly highly across this wavelength range, and so both of them appear to reflect all colors to us. If you wanted to form an image which told you about the locations of these different metals, then you could, for example, choose a wavelength around here in the violet blue. That would certainly tell you where the gold was located, because that would appear very dark compared to the aluminium and silver. If you wanted to differentiate between aluminium and silver, then you could go further out into the ultraviolet, where aluminium is highly reflective, but silver looks quite dark. When we were talking about reflection as a form of scattering, we had some light wave coming in, which was setting up a nice coherent set of oscillations in a bunch of well-behaved atoms. They were scattering, emitting light in all directions, but they were coherently and constructively interfering in just one direction, which gave us the angle of incidence is equal to the angle of reflection law. Now, in Rayleigh scattering, we're again talking about small particles, lambda on 10 to lambda on 15, but they're often in air or in a fluid. So they're randomly oriented, they're moving around, and they're quite far apart. These particles are again going to oscillate. We'll have the oscillating dipole of the electrons compared to the positive nucleus, which is re-emitting the electromagnetic wave in all directions. And we're going to see that this re-emitted wave and the directions that it goes strongly depends on the wavelength. The amount of light scattered is related to the amplitude of the oscillation of the dipole. Now, molecules have electronic resonances in the ultraviolet. So the closer the frequency of the electric field to the ultraviolet resonance, the higher the amplitude of the oscillation. So violet light then is going to be scattered more than red light. And in this expression, you can see that that effect is summarized here as the amount of light being inversely related to the wavelength to the power of 4. The amount of light lost from the original beam is, as you'd expect, related to the density of the molecules and also to the size of the particles as well. Interestingly, it's also related to the angle. So in the graphs down the bottom, you can see on the right how the intensity of the light that is scattered away from the original beam depends on the wavelength in nanometers here. You can see that the violet end is much more readily scattered away than the red end. And on the left, you can see that here is our propagation direction pointing towards the right. So that was the direction that the incoming light came in. And you can see that light that is scattered in the forwards and the backwards direction is more likely to be lost in the forwards or backwards direction. Can you say lost in the forwards direction? It's actually kind of just like put back where it was. And less likely to be sent at right angles to the propagation direction. So in this problem, I want you to use your understanding about the wavelength dependence of the scattering process to explain why the daytime sky, so that's when you're looking at the sky away from the sun, doesn't appear black. Why does it appear blue? And then at sunset, when you are looking through an even greater thickness of the atmosphere, you look directly towards the sun, why does the sky appear sort of reddy orange? This problem's a bit more connotative. We've got white light arriving on the atmosphere. I want you to consider two wavelengths, 460 nanometers and 628 nanometers. And I want you to work out what's the ratio of the amount of light of 460 nanometer wavelength from the sun scattered compared to the amount of light scattered from the wavelength of 628 nanometers. Mie scattering is a more general theory than Rayleigh scattering. It takes into account particle size over quite a large range of sizes, the number of particles, their shape and everything, and some of the effects of these parameters on the interaction of light with these scattering particles can be quite complicated. Mie scattering is useful in that it predicts a lot of things that Rayleigh scattering doesn't. For example, once the particle size gets of the order of wavelength, then the dependence lambda to the power of -4 disappears according to Mie scattering. And that's important because we need to use this scattering for predicting what happens with light interaction with atmospheric things such as cloud and fog, interaction with milk, and with cells and skin and biological tissue. The image down the bottom shows a beautiful contrast between different forms of scattering. The white object in the middle, well, clearly that's an example of Mie scattering. The region around it that's blue, well, we can see the contrast here results from Rayleigh scattering. And down the bottom, we can see there's a green region, and green and brown, resulting from reflectivity that has a wavelength dependence such that it's quite reflective in the green. The polarization of light is another useful property of light that we can use for imaging. In linearly polarized light, the orientation of the electric field is a constant. Its magnitude and sign will vary with time, but the electric field basically resides in the plane of vibration. If we take two orthogonally polarized waves and we make sure that they are in phase with each other, then they will add together to give another linearly polarized wave. And the angle will be a vector sum of their own polarizations. We'll often come across partially polarized light, which has a linearly polarized component, and it also has a component of unpolarized light, where the polarization direction is randomly changing and jumping around, just as we saw those random changes happening in incoherent light. There are a number of ways to polarize unpolarized light. We'll be focusing on one called dichroism. It's essentially selective absorption of one of two orthogonal polarization components in the incident beam. The simplest sort of device is the wire grid polarizer shown on the bottom left. So if we resolve the electric field into the two orthogonal components, we can consider that the X component is going to be able to, the field in that drives the conduction electrons in the wires and generates little currents. And those electrons will lose energy by ohmic heating, so resistance basically. And in this way, energy is going to be transferred from the electric field to this wire grid. There's also the re-radiation of the electrons accelerating in the x-axis, because they'll radiate both forwards and backwards, and that will tend to cancel out the light even more. So there is basically no light being transmitted that has this X component of polarization. So the transmission axis is perpendicular to the wires. The most commonly used linear polarizer doesn't contain wires, but it's actually a molecular analog. So it's got long hydrocarbon molecules which are aligned. Each of these molecules is actually conductive. Dichroism can also be used as a source of contrast in an image. So you can see in these X-ray images, at some particular X-ray energies, one polarization state is absorbed more than the other polarization state, and the image is formed with that information. Malice's law helps us predict what will happen when polarized light is incident on a linear polarizer and the electric field vector is not parallel to the transmission axis of the polarizer. We can then resolve the electric field vector into components that are parallel and orthogonal to the transmission axis. Because the electric field component that's parallel to the transmission axis is given by E0 cos theta, then the intensity of light is going to be proportional to the square of that. In other words, the original intensity of the light times cos squared theta. In this series of problems, I get you to start with unpolarized light and send it through, first of all, one polarizer and then another polarizer, and find out what the final intensity is. I then get you to twist the second polarizer and work out the intensity of the transmitted light, and then insert a third filter in between those first two filters to see what happens. Birefringence is the property that some materials have, whereby light with a certain polarization travels through the material at a different speed than light with the different polarization. This different speed or different wavelength is known as birefringence. They have two refractive indices. It can be inherent to the material or it can be induced by a strain field, and in fact is a really useful way for imaging strain fields in materials. Birefringence, that's the difference between those two refractive indices, is proportional to the strain component, so you can actually get quantitative information. Essentially what happens is that one polarization travels through the medium at a different speed than the other, so one polarization is actually retarded. Now, when a certain amount of retarding takes place, which is going to depend on the wavelength and the birefringence, the effect will be that the polarization of the incoming light, which was like this, will be flipped when it exits the material by 90 degrees. And regions where this has taken place will appear quite brightly when the object is placed between cross polarizers, which would otherwise not let any light through. We started off this course looking at imaging with geometrical optics, but we know that the theory of geometrical optics isn't complete because describing how images are formed in terms of rays is only approximate. We know that light is actually a wave. So what we are going to investigate now is what difference does the wave nature of light make to imaging? We're going to answer this question in a somewhat intuitive method. It applies to a periodic object, but we're going to see that the wave nature of light limits the resolution that we can get. It was first discussed by Ernst Aber in the late 19th century. We'll then discuss transfer functions which can be used to characterize loss of resolution and other effects of optical systems. Aber was studying imaging using a microscope using coherent light. The object, the specimen, diffracts the light, and that diffracted light goes through the entrance pupil. In this case, that'll be the diameter of the objective lens because we have a simple system with no stops. That lens will form the diffraction pattern at the back focal plane. Then these point sources of light emit spherical wavelets in turn, which interfere and some distance beyond will form our image. So you can see we have one and then two diffraction processes. And the important thing about Abbe imaging theory is that it includes the fact that we have a finite sized entrance pupil, which limits the angle of the diffracted light that can enter the system, and that's what affects our resolution. We know that when we have parallel light incident on a grating, which is our object here, we're going to have a number of diffracted orders produced. And each of these orders can be considered as plane waves. And they are refracted by the lens and they converge to points a distance f away from the lens, and that's essentially the back focal plane. The light then continues. It all overlaps once you get to the image plane and forms a complicated interference pattern. And that is our image of the object. An important thing to notice from this diagram is that the size of the lens limits the number of orders that can get through. In this case, we have m has to be greater than or equal to 2 is rejected from our imaging system. So our image doesn't actually contain all of the information that the object was giving. So our object here is a grating. We're illuminating it with collimated light, so plane waves, and it will be diffracting. Each of these diffracted orders is also going to be a plane wave. The angle at which it's diffracted is given by the grating equation. The diffraction pattern would be located an infinite distance away from the object if we didn't have a lens there. Of course, the effect of the lens is to take those plane waves and focus them. And because we're interested in the height on the lens or the aperture where this ray hits, we'll define it as HM, and that will be related to the angle of diffraction and the distance of the object to the lens. Now, diffracted waves are plane waves, and plane waves have an effective object distance of infinity. That means that they will be focused to points a distance f away from the lens, that is f2, the back focal plane. That's where we're going to see our bright spots of the diffraction pattern. Then if we take the ratio of the height from the axis of the lens to the distance to where the image is formed I, we can find out the tan of this angle theta. Now, we know that HM here has to be less than the radius of the lens. That's what we're going to be following through. So let's look at the waves from the first orders, m is +1 and -1. Our ray picture said that they would be diverging from those points. We're using the wave picture, which says we have spherical waves. This is the diffraction pattern. the back focal plane. And what we can see is that this is essentially Young's double slit experiment, where we have 2 point sources of light, which some distance away form an interference pattern. And it's fairly straightforward geometry to show that in order the distance between these maxima is going to be given by d prime sine theta prime is equal to lambda. If we then compare our angle theta prime with theta from before, that was the angle at which the +1 and -1 diffracted orders were launched. What we can see here is that we have what we know this to be the magnification times d. That was the spacing of our grating. So our interference pattern is in fact the image of our object, and the spacing is the magnification times the original spacing. So our grating here, and you can see I've shown what is basically an image and an intensity profile. Forms the diffracted orders if only m is equal to +1 and -1 are recovered by our lens, then our image looks like this. You can see it's got the same periodicity, but it doesn't have the beautiful square sides of our original object. It's been quite blurred out. As we increase the size of our lens and we include more orders, plus or minus 2, they'll interfere together, but because they're further apart, their d prime is going to be much smaller. We'll have higher and higher frequencies included in our final image, and in the next slide you'll see what happens. So our higher order diffracted light. Let's consider m is equal to 2. We know that the angle will be larger because we now have a factor of 2 here. And that also means that the angle at which it converges is going to be larger, and hence the spacing of our orders that arrive at the image plane is going to be smaller. If we work through the algebra here, you can see that it's going to be the magnification times the spacing of the grating divided by 2 in this case. So that's going to be a higher frequency cosine that you're adding to the image, and that means we're going to see more detailed structure in the image. Our original object was, just to remind you, a grating which had an intensity profile like this, and so that meant that the intensity was either 0 or 1. If we include just 0 and plus and minus 1 orders in the reconstruction of our image, we can see that our image profile is actually more triangular. But as we increase the number of orders that are used in the reconstruction of our image, you can see the tops, the bright part, becomes flatter and the sides become more vertical. These images here are the simulated images of the grating, and I have indicated the number of orders that I used in the reconstruction. Now, with the exception of these little rendering errors, these little horizontal bars, you can see that the image of the grating slits is blurry to start off with, but as we increase more orders, it becomes less blurry and the edges of those features become better defined. Now we're going to use a more formal mathematical approach. We'll work in one dimension to keep things simple, and our calculations are going to be based on our wave theory. So the wave amplitude leaving the object is gy. So our aperture function represents our object. The amplitude of the wave that reaches point P on the back focal plane is given by the Fourier transform of gy, which is written here. So this is representing the electric field amplitude at point P. So if, for example, our object is a single slit width A, so we can write our object as rect A, it means that the diffraction pattern is given by sinc beta, where beta is half Ka sine theta. We're dealing with a real imaging system that has a finite pupil, or in our simple imaging system, that pupil is going to be the objective lens. So some of those diffracted components are not going to go through the objective lens, and the radiation field at the back focal plane is not the same as the actual diffraction pattern. So instead of seeing, in our example before, we had a sinc function for our amplitude. Now it's going to be modified. It's going to be cut off at a value of beta max. And mathematically we treat that by multiplying our electric field by some filter function. And that filter function, beta max, is going to be determined by the maximum angle that can go through the lens, or more generally the pupil. So each point in the diffraction pattern at the back focal plane is a source of expanding wavelets. So we can use Huygens principle in order to work out what the field is in the image plane. When that is done, we find that the amplitude in the image plane, that is the image, is the Fourier transform of whatever we see in the back focal plane, the diffraction pattern, or I guess the modified diffraction pattern. This is our diffraction pattern here, and the Fourier transform gives us the image. The image that we see is, of course, the square magnitude of the amplitude. Just to remind you, the angle here, sine phi, is given by sine theta divided by m, where I'm using a capital M now to indicate magnification. That's the magnification that's given by the ratio of the image distance to the object distance. The angle phi is indicated in this diagram here. That's for the m is equal to 1 order. So what this confirms is that the optical image is represented as the Fourier transform of the Fourier transform of the object. So now let's consider how the resolution of our image is affected. Let's say our object is a grating again, and we are only letting the central maximum, so the m is equal to 0 order, through the optical system. What that means is that we have in the focal plane a single point of light which is emitting spherical waves. So in the image plane, what do we see? Basically uniform illumination. We don't see any periodicity, and so we cannot resolve the spacing of our grating object. Now we're going to let just the m is equal to 1 through. Which we achieve by increasing the size of the entrance pupil. And in so doing, in the back focal plane, we've allowed the spatial frequency ky1, let's call it, to go through. So that's equal to k sine theta, which is going to be 2 pi d for the first order. With these two spherical emitters in the back focal plane, we will see, of course, in the image plane, the cosine oscillation. It looks like a blurry grating, so although it's not a very good image, it doesn't look like our beautiful square grating of our object, we can nevertheless resolve the distance between the dark and the bright features. So we can resolve the spacing or the grating periodicity. So for imaging with coherent light, if we want to just resolve something, we need to just allow the m equals 1 order to pass through. That means our angle of diffraction is going to be the half angle of acceptance of our imaging system. And we can use then this grating equation and allow for the fact that perhaps the light is not necessarily traveling in air, because it might be in, say, oil or water, as you might use for an immersion objective in a microscope. Then rearranging this for our acceptance half angle gives us this very useful expression. The smallest possible d that we can see, or the largest possible 1 on d, that is the spatial frequency, is equal to n sine theta over lambda naught. And n sine theta crops up in so many expressions that it's given its own name, numerical aperture, where n is the refractive index of the material in which the waves are traveling. It's usually air. It turns out we don't actually need plus and minus 1. Only one of them is necessary. So we can then halve the size of the lens, as it were. So our other resolution limit is then given by the wavelength divided by 2 times the numerical aperture. So the smallest distance between objects that we can resolve is d, given by the wavelength times 2 n sine theta, where n sine theta gives us the numerical aperture of the lens. If we want d to go down, so we want to see small things that are closer and closer together and still resolve them, then we need the numerical aperture to go up. This is achieved in 2 ways. One is by increasing the refractive index of the medium in which the light is traveling. So we change the air to oil, increasing the refractive index. The other thing is to increase the angle of acceptance. This is so in the top example, where a low power objective is shown to have only a relatively small angle of acceptance compared to the higher power objective, which is closer to the object and therefore accepts a much larger range of angles. This means that with a larger angle, you'll be able to resolve much closer together features. Advantages of including this immersion oil also include the fact that you're going to reduce bouncing backwards and forwards, reflection of light, and you will increase the throughput and get a brighter image. So now some very different imaging. We're going to be looking at distant objects seen with a telescope. Because light has already travelled a long distance, our object distance is basically infinity, then the electric field that arrives here on Earth is already diffracted. So the electric field here on Earth is described by the Fraunhofer diffraction pattern of that object. And so in this diagram down below, you can see here plane waves from our infinitely distant object arriving on our lens. We know that when plane waves arrive on a lens, the lens converts them to spherical waves, which will converge to a point, a focused point, at the back focal plane. So our image plane is also going to be our back focal plane. And as we saw with the microscope, when we have parallel rays or plane waves arriving on a lens and this process takes place, we can mathematically describe this as a Fourier transform of the electric field at the lens. In the microscope, the lens formed the first Fourier transform. However, in this case, the first Fourier transform took place simply because the light travelled so far. So the lens in this case is forming the second Fourier transform. If everything went well, we could get a great image of our astronomical object in the image plane because we would have the Fourier transform formed by the lens of the Fourier transform of the electric field that arrives at Earth, which would simply give us the electric field that arrives at Earth. Unfortunately, we have to take into account the fact that we have a spatial filter function from the telescope. Well, then that modifies the diffraction pattern that we're Fourier transforming to collect the electric field in the image plane. So we can either take the product of these things in Fourier space, Fourier transform it to work out what our image is, or we know that if we multiply in Fourier space, we can convolve in real space. So an alternative way to describe this is our image is going to be the electric field of the star convolved with whatever that spatial filter function is in real space of the telescope. Let's look at the diffraction in a bit more detail. Here's our object. It's a circle. And if I go along this x-axis here, I can plot the intensity as I go along. And you can see that I'm showing it has a very abrupt change from 0 intensity to maximum. The Fourier transform of an object like this, a two-dimensional object, is known as airy rings. We have a bright central patch and some fading rings outside of it. If I run through the x-axis here, you'll see that the intensity looks a little bit like a sinc function. And this central region here is known as the airy disk. We know that for a diffraction pattern, the characteristic size of that diffraction pattern, which we can measure with the y-coordinate, is going to be proportional to L, which is the distance that the light has travelled. If we're talking about astronomical objects, then L is enormous. So it means that y coordinate is also going to be enormous. So here on Earth, the part of the airy pattern that we see is just this little bit up here. It is, as you can see in this graph down here, essentially flat. So we have a uniform irradiance over our objective lens. Unfortunately, we can't use all of even the airy disk to create our image. So what we do is we cut it off. We only use part of it. And that's because we have a finite entrance pupil. Our telescope only has a finite size. So if we multiply the aperture function of our telescope with that electric field, then essentially what we have is something that's proportional to the aperture function of our telescope. And this is because we have a circular lens, I'm assuming. It means that when we take our second Fourier transform to get our image, we see the Fourier transform of that top hat, which is the airy pattern. So our point object is imaged as the airy pattern, the diffraction pattern of our lens. If we increase the size of our lens, then we will decrease the size of the airy pattern. As you know, diffraction patterns have a size that is inversely related to the characteristic size of the aperture. Because in general, the angle of diffraction, sine theta, is going to be proportional to 1 over d, where d is going to be the characteristic size of the diffracting object. In optics, this is known as the point spread function. It has its analogy in electronics as the impulse response. The point spread function of an imaging system basically describes what happens when your input to the system is a point, that is a two-dimensional delta function, and we use it to predict the output of the imaging system. So unfortunately, our point object is not imaged as a point. It's imaged as the diffraction pattern of the circular lens, and that's because our lens is acting as a spatial filter to the diffraction pattern from the distant astronomical object. When we have a point object, which mathematically we would write as a delta function, and we input that to an imaging system, then the output is known as the point spread function. And we're going to use for that the coordinates x, y, which are the coordinates of the image plane. Now, around the same time that Ernst Aber was looking at objects under his microscope and considering that a complicated object could be described as a sum of different gratings with different spacings and angles, which would create diffracted sets of plane waves, Lord Rayleigh was considering that a complicated object could be made up of points. Each of these points would emit spherical waves. The role of the lens was to make these spherical waves converge to image points again. Both scientists saw that the problem was there was a limit to the extent of the imaging system, and that would either mean that some of the diffracted orders couldn't get through, or it would limit the extent of the spherical waves. Because of this, it meant that the final image was not going to be the same as the original object because of the loss of parts of those wavefronts. In Rayleigh's theory, he showed that the ideal image point was going to be the Fraunhofer diffraction pattern of the exit pupil. More generally, we would often write the aperture stop. Still, we've considered here that the electric field, which is the superposition either of plane waves or spherical waves, depending what mood you're in, is always going to be modified, that is multiplied by some kind of aperture in the imaging system. And that's best case scenario. There could even be other aberrations which are worse in your imaging system. But that's something that we've discussed another time. An important assumption that we haven't yet made explicit about Rayleigh's theory is that two neighbouring points on the object emit independently of each other. That is, they emit incoherently. This is in contrast to Aber's theory. He was looking at objects under the microscope, and in that case, illumination is usually closer to coherent than to incoherent. However, for astronomical objects, you would expect that one star would emit quite independently of another star. Now, the effect of this incoherent illumination is that we will see the airy pattern from each of our objects, but what we won't see is any interference effect between those two objects. So a cosine or something like that is not what we see. We just see a completely normal sum of the intensities. Now, according to the so-called Rayleigh criterion of resolution, we're going to just resolve two incoherent point sources when the center of one airy intensity pattern generated by one point source falls exactly onto the first zero of the airy pattern generated by the second point. So the minimum resolvable angular separation of these objects is given by this expression here. The 1.22 comes from the position of the first minimum in an airy pattern. Diagrammatically, that looks like this. So the diameter of our system is d, and the minimum angular separation, theta min, is given by the expression that is listed up here. If we want to know about this distance here in the imaging plane, then we can notice that the distance between the lens and the image plane, I, is going to be f. So that means that our y is going to be 1.22 times the wavelength times the image distance, which is f, divided by d, which is, notice that we have this ratio f on d, 1.22 wavelength times n, the f number. A classic way to characterize an optical system is to image a resolution target. That's a target that has a number of features on it that get finer and finer. In the image, eventually these features become so fine that they can no longer be discerned. Now, whether or not something can be resolved was given, at least in Rayleigh's criterion, as either a yes or a no. But we can probe that a bit more subtly. We can use this useful parameter called contrast or modulation, which is given by the difference in the image irradiances, so the maximum and the minimum, divided by the sum. Now, contrast, instead of being just a yes or no, can take a continuous value. Optimum contrast, where the maximum irradiance is very, very bright and the minimum is 0, dark, is going to give us a contrast of 1. A contrast of 0 means that we can't see anything at all. On the left-hand side, I show a bar target resolution chart. You can imagine in the original object, as I travel across one of those many targets, you will have a contrast that is a maximum. That will be the input to our imaging system. The output contrast will not necessarily be 1. Furthermore, we know when we reach some kind of resolution limit, then the contrast is going to go way down and we won't be able to resolve things anymore. So you're already familiar with the idea of treating the object as the source of an input light wave and treating that input light wave as the superposition of a number of plane waves which travel off in specific directions according to their spatial frequency. By measuring the contrast of the output of our imaging system for different spatial frequencies, be they low spatial frequencies or high spatial frequencies, we can get an idea about how the system modifies the amplitude and phase of each plane wave as it transfers it from the object to the image. So the diagram on the right shows the output contrast plotted as a function of spatial frequency for some hypothetical system. It starts off with a DC value of probably 1 and crosses the 0 axis somewhere where it can no longer resolve the data, and that's our limiting resolution or cutoff frequency. This plot of the contrast transfer function is sometimes called the modulation transfer function. Now, what affects this contrast function? Diffraction obviously is going to reduce the contrast. Aberrations will also affect the contrast, and even simply poorly centering the optical elements is going to shift the position and destroy the contrast to some degree. So the contrast or modulation transfer function captures all of those things that happen in the imaging system. The contrast transfer function is widely used as a means of specifying performance of all sorts of systems and elements.